Could you explain the concept of negatively curved crystals and its importance in simple terms, where the universe is envisioned as a periodic crystal that is warped into a negative curvature by gravity?
The idea of thinking about the universe as a negatively curved crystal, this is really just a metaphor. It's not something I want to impose on physics. It's a way of helping people to visualize what three-dimensional shapes look like from a mathematical perspective. Nevertheless, there's the thinking, pursuing this physical analogy, I think, is very profitable. So we all understand what it means for a surface to be positively curved and for a surface to be flat. And with a little more thought, you can imagine some sort of negatively curved surface like a saddle shape. But it's much harder for us to wrap our minds around what it means for space to be curved. Even positively curved space, which should be familiar, like a sphere, is hard to imagine. What I'd like to do is give you a way to think about this difference between positive, flat, and negative curvature. And that gives a hint about why, when you look on the menu, there's so many more negatively curved examples. Okay, so the difference is this. On a sphere, in a positively curved space, you can have two line segments that go off in different directions and then they converge again, right? If you start at the North Pole and you go off in any two different directions, you'll meet again at the South Pole. So there's a sort of a reconvergence phenomenon. In flat space, we don't quite have that, but there is the notion of parallel lines. There are lines that start out a bounded distance apart and they stay a bounded distance apart for all time. And the big difference in negatively curved space is this, is if you try to construct two lines that are parallel, they start out in the same direction, but they're at slightly different locations, then they rapidly move apart from one another. So that's what negative curvature looks like. It does not behave in the same way as our more familiar Euclidean spaces. So let me just, in case this is helpful, let me just share a couple of images with you. So this is an image of our familiar flat space. This is an actual, it looks, like computer graphics, but it's an actual piazza in Tuscany. And you see these parallel lines going off to the horizon. The horizon itself is a straight line. There's a certain way, though, in which, although this looks infinite, or it approaches infinity, or it gives intimations or hints of the idea of an infinite plane, it's a little bit limited because of this parallelism. If you go out, for example, n generations in this checkerboard tiling, you only see about n squared of these tiles. But let me go to this Escher print that I think many people are familiar with. Well, before I do that, let me just show you a tiling in negatively curved space. So this is, I'm doing 2 dimensions here instead of 3 dimensions, but this is to give you the idea. So just as we have right-angled squares in 2 dimensions, you can make right-angled pentagons in 3 dimensions, and you can make checkerboards or infinite tilings where you piece together pentagons rather than squares, which is very weird because we can't use pentagons to make clean tilings in ordinary 2-dimensional space. But in negative curvature, you can. So this is a picture of an infinite negatively curved plane, and you have to kind of adjust your eyes to imagine first that these curved lines, they're actually straight in this geometry. It's only sort of an artifact of perspective that they seem to be curved to us. Actually, the lines are straight, but the space is curved. And the second feature is that all of these pentagons are, in fact, exactly the same size. You might say, well, that's ridiculous. Obviously, the ones near the boundary are small, but of course, if I go back here, the distant squares also appear to be small. It's really just a feature of perspective. So you should try to visualize that this is an infinite tiling. There's infinitely many tilings, and they go all the way off to this horizon, which is the circle at infinity. Okay, so a more persuasive version of this picture is this famous Escher print, which is an entire negatively curved universe filled with angels and devils. And one of the features I want to draw to your attention is, first, there's this kind of divergence that I was mentioning, which is that if you go off in different directions, you very quickly see a huge amount of angels and devils intervening between, say, a vertical line and a line that goes off at 120 degrees from it. There's an enormous amount of angels and devils packed into this region. And in fact, if you were to go out, say, n generations in this tiling, instead of seeing like n squared devils, you would see something like 3 to the n devils. So what happens in hyperbolic space is there's enormous growth of volume or area as you expand the radius of a sphere. And to accommodate that, radial lines have to spread apart very fast. Okay, so that's a little glimpse into negative curvature. Okay, now what I want to do is take that as a point of departure to explain why negative curvature is so much more versatile than positive curvature, and why most three-dimensional spaces are negatively curved. And it's kind of like this. So imagine 3 different styles of writing a mystery novel. So one style is all the books begin the same way and they all end the same way. And then there's something that happens in the middle, but you know what the beginning is and you know what the end is. That's kind of like positive curvature. It's a fairly impoverished set of narratives that can be written in that language. Now, in flat space, you have this notion of parallel lines, and that's kind of like having a novelistic style where the plots are different, but they all follow the same pattern. Maybe they don't have exactly the same beginning or end, but they're predictable. And the main thing about hyperbolic space is that it's not predictable. This divergence of geodesics means that if you start heading in a direction and somebody tries to follow you, if they go in a straight line in a slightly different direction, very soon you're in very different parts of the world. You've diverged rapidly. And this is like having a detective novel with lots of plot twists, with surprises coming constantly, twists and turns. And the number of such novels is much, and their form is much richer than the kind of narratives you can have in the other 2 types. And this is very much what happens in negative curvature. The positive and flat spaces are kind of confining, and the negative spaces open up many more possibilities for space to sort of branch out and then reconnect with itself. And that's why most three-dimensional spaces are negatively curved. That's at least an impressionistic explanation.
What types of patterns created by the thin walls of the crystalline structure might be visible in the night sky?
So here's some kind of array of many different patterns. This you should think of as, when you look out on the night sky, you see a sphere. I've kind of turned that sphere inside out so that you can see many different patterns at once. So these are kind of globes of constellations that might appear to give these periodic patterns in the night sky. One of the interesting things is that if you study traditional chemistry, you learn that there are something like 200 odd possible patterns for crystalline molecules in the chemistry of our physical world. But in negatively curved space, there are infinitely many possible crystalline patterns. And so I spent some time drawing pictures to give people just a glimpse of these patterns, but in fact, there's an infinite array, and it's very interesting to even try to organize what all the different shapes could be. One of the reasons there's infinitely many patterns is very simple. It's that in our world, actually the strange thing is that in our world, there are so few patterns. So if you want to cover a floor with tiles, you could use square tiles, you could use rectangular tiles, you could use equilateral triangles, but there's not really that many different motifs. And if you want to make a symmetric tiling, it's known that there are 17 different types of wallpaper patterns, kind of periodic ways you can put figures or tiles on a wall or on a floor. And of course, the most familiar are squares and rectangles. And the reason squares and rectangles are so important is because 90-degree angles are very useful when you try to fit tiles together. And if you want tiles fitting together with 90-degree angles, in our space, you can only have 4 of them. And then that kind of forces the tiles themselves to be rectangles, because if you have a figure where all the angles are 90 degrees, it basically has to be a rectangle. Okay, now what happens in negative curvature, as I just showed you, is that there are pentagons where the internal angles are 90 degrees. That's very strange. And you have to make the pentagon exactly the right size for it to have 90-degree angles. So you can't just buy them at the store in any size. In negative curvature, there's a characteristic length scale, and at some length, pentagons have 90-degree angles. But at a longer length, octagons have 90-degree angles. And at a different length, you can get 12-sided figures to have 90-degree angles. And so you can get figures with infinitely many different numbers of sides to serve as the fundamental motifs for periodic tilings. In other words, already in 2 dimensions, there's infinitely many possible crystals. And it really just has to do with the fact that in our dimension, that once you start increasing the number of sides, you sort of hit the hexagon. You can tile your floor with hexagons, but you can't tile it with 7 gons. But in negative curvature, you can, and you can do all the integers past 7. And so I have a movie I'd like to share that kind of illustrates this. Here again, we see a sort of a crystalline structure that's based on negative curvature, and there's some number that plays an important role here. The number turns out to be 7, and as you increase this number, you get a whole family of circle patterns, which look similar to each other but are not exactly the same. And so you see this existence of infinitely many different circle patterns. And there's even a limiting pattern where in the pattern we starts out with has circles that don't touch each other, and in the limit, these patterns do. So this movie is actually showing you not a continuously changing image, but a sequence of images associated to the numbers 7, 8, 9, 10, getting larger and larger and larger and converging to infinity. And one thing I want to emphasize about it is one of the things that's really interesting is that this original figure, this pattern of circles, is what people often call a Swiss cheese. It has the interesting property that none of these circles touch each other. And it was a challenge for many years to find a good way to draw these concrete crystalline mathematical objects that everyone knew about where the circles don't touch. And the limiting picture where they do touch is much easier to draw. In fact, it's famous. It has a name. It's called the Apollonian gasket. And what this short movie is illustrating is that Apollonian gasket can be thought of as kind of the terminal situation of an infinite family of patterns.